So, can people hear me if I stand here? Is this all right? Great. So I'm going to talk about lifting network data stores out of kernel memory with MirageOS and Irmin. So when I talk about network data stores, I'm not talking about like big arrays of disks or RAIDs or anything like that. But what I mean is these small bits of state that hang around in network stacks. Even really simple network configurations have a whole bunch of state that's underlying a lot of the pieces that make your network work. The examples that I'm going to talk about most in this talk are caches and map tables, which are generally just of the form of a key value store with some expiration attached to them. This form happens a lot when we talk about network state, and there are also some more complicated things that we can look at. Do more with that. So, just in case anyone in this room is not familiar with either of the two things that I've mashed together and then decided to give a talk about, MirageOS is a library operating system for constructing unikernels, which are minimal single application virtual machines. Something that's really cool about working with Mirage is that all of the code that provides things like networking and storage is fundamentally the same kind of code as your application code. And so this means that instead of having this kind of data locked up in kernel memory where you can't look at it and you can't do anything with it, suddenly this is the kind of code that you can work with as an application person. And you can decide, for example, that I want to make whatever a certain kind of API for something like an ARP cache. Or I can expose the entire ARP cache to other things that are running in my process space. But that starts to look like shared mutable memory, and that's not really a great idea. So you need something to help you with making this be not a really awful decision. And that's why I also want to talk about Irmin. So Irmin is a library for persistent stores, which has built-in snapshot branching and reverting mechanisms. Irmin provides us sort of a nice way to mediate and track access to these data structures, and it also gives us, it's also type aware. So when we're working with stuff in Irmin, you can be aware of the fact that, for example, we're operating over IP addresses, we're operating over MAC addresses, or we're operating over some gigantic record that represents the type of the TCP connection. When we interact with Irmin, sort of the structure of this is essentially Git-like. So when we want to make some kind of update, the sort of process that we follow is we'll clone some new branch from some authoritative state about what the world should be. We'll make edits to our own branch, and then we'll try to merge the branch back into our primary store. So for people who've worked with Git before in this room, it might not seem all that attractive to make this kind of data flow be the center of something really important, like whether or not your network works. Because you probably had it happen before that you've gone to make some change to source code, and you've ended up with this situation where you have a merge conflict. In this particular example, this is just a small example of making two different branches off of some primary branch, and then having two different edits to the same line of code, and then trying to merge these two edits back in. It might not be very visible, for which I apologize, but the actual code in this example is just there's been a change to some constant that's being passed to a function, and then there's been a change to the name of another thing that's being passed to this function. And these two edits are not actually mutually exclusive. It could, if it were aware of the fact that these two things are don't necessarily conflict with one another, it could resolve this conflict automatically. And that's because it just wants to operate on the level of a line-by-line diff between source files. It can't resolve this for us. And it basically holds up its hand and says, I need an adult! But we can do better than this if we know about the structure of the things that we're trying to operate on. So this is something that's really nice about Irmin. Sorry, that's a bit early. So Irmin is aware of the types of the things that we're storing, and it also lets us define our own merge functions that can use this information about structures to make intelligent decisions. So in this case, for example, if we had some structural information, we could just say, okay, these things aren't that different, we can just make both of these changes and that's fine. I'm going to motivate this a little bit more with a different example, which is, I mentioned ARP caches earlier, they're just a way of mapping IPv4 addresses to MAC addresses, which is basically just a number to another number. Eventually it should expire. In a network stack where you're actually using this, you have potentially multiple code paths that are trying to access this store. So usually you'll have some thread that's responding to incoming packets on the network, which are saying, hey, I want you to map this particular IP address to this MAC address. You also have probably some process that's doing expiration on all of these entries, so that when they've been sitting around for a while, they haven't gotten an update, they get thrown out of the store. And you're also probably actually trying to provide some service for some part of the stack upstream. So respond to lookup requests and that sort of thing. So in the case of an ARP cache, the rules for how you can resolve merge conflicts are actually really simple. Because for example, the only way that anything should ever leave the cache is if it's been expired. And you always want to favor newer entries. So in this case, you can write a merge function that's really, really simple and probably kind of illegible. And not really able to be made more legible, so I apologize for that. This is just a really simple merge function that we can pass directly to Irmin that says, in the case where I have a merge conflict between two entries which are values for an IP address to be mapped to, I want the one in the case of a merge conflict between something and nothing, I always want something. In the case of a merge conflict between something old and something new, I always want something new. That's it. No merge conflicts. You're good. In this particular case, we don't care about the history, but if we wanted to care about the history, we could. Irmin lets us also consider what the previous ancestor of both of those changes was. In this particular case, and in all of the cases that I'll discuss, for the things that we've implemented with persistent networking, we don't need to care about that, but for more complicated cases, we could, and it's free. So I'm going to show you a quick example of something else that you get when you use Irmin. Irmin is nicely abstracted between different backends. So one of the backends that you can use is simple in-memory store. So you get the same abstraction of different branches and history that's saved in Irmin, but this is just it's just held in memory within your application. But you can also use a backend that represents this information directly as a gate store. So I'm going to show you sort of the implications of what happens when you do that. So, sorry, I had intended to present this on a different computer, which someone walked away with a couple hours ago, so you can bear with me, I appreciate it. So what I'm about to show you is just a quick demonstration that's written with MirageOS. Using Irmin as a backing store for the ARP layer of a whole bunch of virtualized network nodes, which are going to talk to each other on a network. So I'll launch this, and they'll begin speaking with one another. I'm going to suspend this process really quick, and then I'll show you what the Git store of all of these nodes looks like. So we have 10 different network nodes that are all saving all of their ARP information in a Git store, and this is just a common visualization tool for Git stores. So if we scroll down, we can see at the time of network initialization, a whole bunch of branches as each of these network nodes comes onto the network and sends a broadcast saying, hello, I'm here, my IP is whatever, my MAC address is whatever, I want you all to know me and recognize me. And all the other nodes say, okay, I'll write that down, thank you. Branch, 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 branch. And then as the network calms down, everything gets merged back in. Things are a bit calmer. Everyone's just ticking along looking for expiration. So this is kind of a nice way to see. For example, you can imagine loads of uses for this in debugging, right? So you have the execution history of everything that's happened to all these stores available to you right here. You can see, for example, the content of all of these changes. Here's for example the exact change made by one particular node when it's updating something in the cache. Something else that you can do that's potentially interesting. Let's start that again. Is you can also clone the store and do stuff to it manually. So I'm going to clone the contents of that store that I showed you. So I now have my own copy of all of this information. So for example, I can see the status of one of these nodes are cached as of the time that I cloned it. So I can see all of these individual entries. And I can make changes to it as well. So for example, if I've decided that I don't want that thing to have anything in its ARP cache, I can do that. And then I'm going to do, so it's a bit difficult to commit quickly enough on the command line to, because all these nodes are updating, are making commits all the time, it's a bit difficult to simultaneously have everything and then push stuff. So I'm just going to run this this command here, and it'll probably take a couple tries, just to warn you. Oh, actually, there we go. So, so if I start up, so I made my commit, and if I start up, if I start my visualizer again, if I start my visualizer again, I should be able to see the changes that I made. See, that's me. I'm not a node on the network, I'm a human. I can see my changes that have been merged in. If I were to scroll down far enough, I'd be able to see my commit message, but it's a bit difficult to find, so I hope that you'll trust me just based on that merge message. And then I can see as well that change has caused the server to issue some queries. So these are the particular commit message that we see here is that in response to a direct query, we got an answer back as opposed to part of a normal update procedure. So we can see changes that we can see basically responses to the changes that we made. Another thing that's kind of cool and sort of extremely related to the Textoro talk is I've forgotten. There we are. So if we actually kill off this process, all of this state stays resident. We can continue looking at the we can look at the state of the world as it would kill the process, and all of the historical information is still available to us. I'm going to show you as well another demo really quickly, which is interactive. For those of you who felt like today is a long day, and you haven't made enough of a mark on the world, and you just want to express yourself in some way that involves sending packets on a network. I feel you. I understand you. So this machine that I have here, which I'll try not to disconnect, I'll show it to you. It's just a little ARM board that is running the Zen hypervisor and therefore capable of running Mirage kernels. So what I'm doing right now is I'm setting it up to, it has a Wi-Fi interface and an Ethernet interface. And what I'm doing right now is setting it up to provide a wireless network with the SSID free Wi-Fi for humans, not a trap. It's a little bit of a trap. So, the next thing that I'm going to do is start a Mirage kernel that has a network interface on both sides of basically both sides of this QB board. So it has one interface that's facing the Ethernet, and it has one interface that's facing the Wi-Fi. And for any client that's on the Wi-Fi, it will take the packets that are coming in and rewrite them to look as if they're coming from the QB board. This is basically the same technology that's in any commercial phone router that you might see. And this is basically the technology that occasionally you have to remove when you've been torrenting too hard and it just can't take it anymore. But this one's all about count. So another thing that this particular unit kernel is doing is it has in addition to the two interfaces that I mentioned, it also has a management interface that's running an HTTP server that's providing access to the Irmin store. That's powering all of the NAT translations that are happening with packets on this network. So, if anyone has felt like they need to make a mark on the world and join this network, we can see via that web interface a nice graph of additions to the table this is being updated in real time as possibly my phone, possibly someone else's phone, possibly someone's laptop is trying to go out to the internet. And we can also see, this isn't a very helpful thing because it's just showing us the commit messages, but we can also get a list of all of the entries in the table. Assuming that it hasn't already crashed from having too many. It doesn't claim to be out of memory. Demos, folks. There we go. So we can see that someone is very enthusiastic. Very, very enthusiastic about resolving some names. Like, they're really super into resolving some names. Just like, yeah, lots of name resolution going on in here. So this access to this particular store may seem kind of boring. Like, okay, so great, you put some stuff on the screen, that's awesome. But having worked with network devices myself, usually this is buried way deep in kernel memory, and there's just nothing that you can do with it. Even in Linux, most of the which is the underlying implementation of most of the things that you can buy that will do this. Even in Linux, the best interface that you have for this is the command line utility IP tables. This is so many leagues better than this, and the fact that we can expose this database means that we can write applications that are going to do intelligent things with this data based on other things that are going on in the stack or in application space. I'm going to navigate away from that before it crashes and embarrasses me. So, for example, the two things that we've seen so far, we've seen something that keeps track of mappings between IP addresses and hardware addresses. We've seen something that makes mappings between IPs and other IPs. Traditionally, what happens in a network like this when an IP changes is there's no kind of feedback between information about the change of that IP and stuff that has that IP stored. So usually, what happens in networks, if you have a local IP that changes, is the client just has to wait for all of its connections to expire and then go make some new connections. That sucks. But if you have access to both sides of this information, you could really easily imagine, for example, I want to react to a change for an IP address in the ARC table by updating all of the mappings in the map table. So suddenly you have this totally transparent change that happens that the user doesn't even have to know about, because you can make your stuff work together without worrying that these out-of-band changes are going to just totally destroy everything. Some issues with doing all of your network data stores in Irmin. The tagline for Irmin is that it's the database that never forgets, which, when you have a finite amount of memory, is maybe not your favorite thing in the world. Irmin will preserve the history for the entire store until the heat death of the universe, or it runs out of memory, whichever one comes first. There is a garbage collection planned for Irmin, but it's not there yet. So pretty much any application that would use this currently has to be aware of this, and the user pretty much just has to be prepared to go in and hit a switch every now and again. As I said, that's planned to change soon, and I'm looking forward to it a lot. Another thing that's currently not really very well handled is fine-grained access control. So you can choose to expose these stores in a number of ways. For example, you can give blanket access through Git. You can give blanket access to this HTTP interface. But what you can't do is say, for example, I want someone to be able to access only this part of the Git FS that I'm exposing through Irmin, or I want someone only to be able to read and not write through the HTTP store. You can get around this in really coarse-grained ways, like, for example, exposing the HTTP interface only if someone has like a client certificate. But there's not really a great story for that yet. Another question that people have asked about this, which is a very reasonable question, is what about performance? You're suddenly doing all of this extra stuff in basically the hottest part of a hot loop of a thing that you want to probably have be reasonably fast. And I was quite curious about this as well. So I ran some tests that use some of the same code that you've already seen in demo form, basically to attempt to compare the latency of the performance of an Irmin store versus the performance of a simple hash table. So here are some numbers for the hash table implementation for NAP. Maximum latency, the latency between lookups and insertions is fairly differential, so I've broken those out differently. It's on the order. It's around the worst that you do is around 150 microseconds for lookups and 500 for insertions. And as you can see, as the table gets larger, you start to see some problems. And this is with a 32 megabyte unit kernel. So you do start to see some garbage collection pressure as the size of the table increases. The numbers for Irmin are not that much worse for lookups, and they're getting better. I would ask that anyone who's looking at these numbers interpret them as a ceiling and not a floor, because all of these, as it says here, the maximum latency for lookups is 220 microseconds, down from 450 last week. So, yay. For insertions, it's 10,000, but down from 25,000 yesterday, so we're doing well. All of these changes are from changes in my implementation and not from changes in Irmin. So as I said, you should look at this as a ceiling and not a floor. Someone who knows a little bit more of what they're doing could probably do better than this, but we're seeing sort of similar. We're seeing a similar pattern, but for different reasons. Where as this has the table is ugly, we see generally worse performance rather than these occasional GC pressure outliers. So there are further things that you can do when you have all of this state exposed somewhere that you can go and grab it. For example, XenStore, the key value store for the Xen hypervisor, has an Irmin implementation. So you can imagine really simply putting all of this data about your network and how your network is doing directly into the hypervisor store, and then being able to persist it when you have a machine that's down, or move it across different hypervisors. So that's pretty much all I have to say about that. I'm happy to take your questions, and thank you for listening.
I apologize if I missed that earlier. When you showed the merge function,
Yeah.
when you have a merge function, do you give both untouched blobs, or do you insert some kind of a merge pattern like it does? Do you assume that the data is text, maybe insert some kind of a...
So you're actually past something of the type that you defined to store to be. So when you say I want an Irmin store, you say I want an Irmin store with keys of type this and values of type this. And so what you get, what you're looking at when you're in that merge function, is you're actually for the case that I showed, where your keys are IP addresses and your values are a tuple of MAC address in time. What you're looking at is actually a tuple of MAC address in time.
So they both modify, right? There's no...
Yes.
Thanks again.